Perfect. Okay, let's jump to the next one, which is stability of rock and concrete armory units. I think you already discussed this topic a little bit with Professor Archetti. And the reason why I am insisting on it is that I want to make some considerations on the physics of the process. And in order to do that, I am introducing a method for analyzing the stability of rock and armor units, which I don't think Professor Archetti mentioned. I hope so. But if yes, if you already know the Shields method, just let me know, and then we discuss it anyway. But are you familiar with this term, Shields method, for analyzing the stability? Okay, let's see. First of all, it is once again a problem that is characterized by a lot of complexity, because here we are talking about armor units that form shapes like breakwaters or groins, and these are made by typically rubble mounds, which may be rocky stones or tetrapods like you see in this picture. And the question is whether they are stable against the forcing operated by waves. So it is, as you understand, a problem with a geometry that is much complicated. The forcing is chaotic, it's random. So there is a relevant random component in that. And also the conditions are varying, because depending on the season, the temperature, the rocky units may be covered by some material that makes them slippery. And so it's indeed a problem characterized by a huge complexity, and this justified the application of empirical formulas. So this is why you mainly studied formulas that are empirically derived, typically basing on lab experiments. But today I would like to focus on the physics of the problem. And in particular, let's try to analyze what is the physics of a particle that is placed over a slope that is subjected to forcing operated by waves. So if you look at this figure here, and let's use also the blackboard. Let me see. I need to take the markers, and let me see if the camera is well placed. Yes, the camera is okay, but I would like, for the benefit of who is attending remotely, change the camera. Let's see. Okay, very good. This is much better. Okay, and give me 1 minute that I take the marker, because the figure is already much developed, and I want to remake it from the beginning. Just 1 second. Okay, so let me put the figure on the screen so we see. I try to use the same symbols. Now, the problem is simple. We have a slope, which is the slope has an angle beta, I think, yeah, in the horizontal plane. So we have this slope with Armory unit. Let's make it with a simple geometry that is placed over it. Good. This is the Armory unit which we want to study the stability. And there is a forcing here operated by waves. Okay, and the forcing is given by F, is given by a coefficient C2, which depends on the shape of the unit. And then we have a symbol tau, which is the shear stress. It is the shear stress operated by the current on the bottom and on the unit. It is a tension. And then we have a characteristic dimension D, which may be, if this was a cube, D is the side of the cube, squared. Why squared? Because the forcing is proportional to the area of the surface that is invested by water. And therefore you square the characteristic dimension. And the shear stress is given, you can imagine that it's proportional to the square of the velocity. And the shear stress basically is given by the fact that if you flash water over a surface, and especially over an obstacle that is placed over the surface, then the water flushing gives a force, originates a force against the form that is placed on the surface. And this forcing is proportional to what? To the dimension of the area invested by water, is proportional to the shear stress, which is force per unit area, it's a tension. And then there is a coefficient that basically depends, as I said, on the phase, on the shape of the particle. The forcing is directed upwards when there is the run up and downward when there is the run down. Actually, we consider here the case in the figure where the forcing is directed upward. It doesn't change much, as you will see. It's just a minus sign that is converted to a plus. That is to say that usually during the run-up, it is the phase where we have the greater forcing, because the shear stress is much higher, because the velocity of the run-up is higher with respect to the velocity of the run-down. The run-down, you understand, there is water stopping, and then it comes back, but still the velocity is much reduced with respect to the run-up. Okay, and this is a destabilizing force. And then there is a stabilizing force. What is the stabilizing force? It's the own weight. It's the self-weight. So the self-weight, let's put it here. Let me see if in the figure I applied it, yes. The self-weight, of course, it's vertical. And what is the first of all, let me say that the self-weight can be decomposed in a component that is parallel to the surface and a component that is perpendicular to the surface. The parallel component is actually a destabilizing force. The perpendicular component is stabilizing. So let's put in evidence these two components. So we have one here that is parallel to the surface and one here that is perpendicular to the surface. I called them, okay, I just, if this angle is indicated with beta, this angle here is equivalent to beta. And the parallel component is given by, if I call the self-weight W, so it's a weight, it's a force. I indicate it with the symbol W. The parallel component is W sin beta. Okay, the side of a rectangle triangle is given by the W, which is the longer side. I don't know how to say hypotenusa in English, times the sin of the opposite angle. Okay, and this one here is W cos beta. W cos beta. Okay, perfect. Now we have to make a balance of these two components, and then we can say that F minus, and here I put a minus, and because it's there and up, F minus W sin beta is equal to what? Is equal to W cos beta tan phi. Let me see if the symbols are okay. Yes. Why tan phi? What is tan phi? Phi is the friction angle. And you know that if you want to estimate the friction originated by a vertical component, you have to multiply the vertical component, the vertical forcing, which is W cos beta, the vertical forcing, by tan phi, where phi is the friction angle. We can substitute for, instead of F, we can write, I write above here, C2 tau d squared minus W sin beta is equal to W cos beta tan phi. Very good. Okay, now what I want to do, I want to find an explicit representation for tau. Why? Because I want to find the value of the shear stress that is so-called critical, which basically corresponds to this equality here. You understand that when the destabilizing forces are equivalent to the stabilizing forces, you have a critical situation. You have an equilibrium such that even a small perturbation that causes an excess of the destabilizing forces would move the particle. Okay, so from this equality, which expresses equilibrium, I want to compute the shear stress that brings to equilibrium. And therefore, I have to find an explicit representation for it. Perfect. Now let's write here. We can write that C2. I am making it step by step because in the web pages there is already the final result. So C2 is equal to W cos beta tan phi plus W sin beta. And then I can write that tau is equal to W cos beta tan phi plus W sin beta divided by C2 d squared. Very good. Now let me express W in this way. W is equal to the immersed specific weight of the unit, which is gamma s minus gamma. So we assume that the unit is immersed, which is a conservative assumption. And then we multiply it by the characteristic dimension cube plus a coefficient C1, which is a shape coefficient. Again. Okay, perfect. Now we can substitute here, but before substituting, I delete here. Before substituting, let me rewrite this in this way. Tau is equal to, I divide the numerator and the denominator by cos beta. So what I can do is I put C2 tau square cos beta, and then I take W tan phi plus W tan beta. Just follow my development because it's a bet, you know. We need to check if I reach the same formulation that we find on the web pages, and then I can substitute here.
Just a question. Like whether is tau at the denominator?
No. D square. Sorry. Is this fine now? Yes, I think so. But actually, let me think. I'm not sure if this is correct, because I think cos beta should be here. Should be here, or not? Let me see. Cos beta.
Yes.
Yeah, correct? Yeah, should be there. Should be there, the numerator, not the denominator. Because here, if you look here, it's W tan phi cos beta, and then see, it is like this, I think. Are you convinced?
Yes.
Let's move forward, and then we will see, because there is the final result on the web pages. This is just a mathematical development, but okay, now let's write tau is equal to, I can, to simplify things, I think I can write it in this way, cos beta divided by C2 d square, which multiplies, I can take a common factor W, so times gamma s minus gamma d cube C1, which multiplies tan phi plus tan beta. Okay, we are almost there. Now, let's write here. We can write that, first of all, let's put C1 divided by C2 equals C. These are shape coefficients. I didn't mention that C2 is called the drag coefficient, but it depends on the shape. Okay, so basically I can write that theta is equal to tau, sorry, not theta. Tau is equal to C gamma s minus gamma b square, okay, times cos beta divided by d squared times tan phi plus tan beta. Okay, and okay, very good. Now here I have these two annihilate, and then I can write this here below, which is the final result. Let me write it in this way: tau divided by gamma s minus gamma d is equal to constant. Why constant? Because if I assume that the C, which is a shape coefficient, is constant, I can say that the friction factor is the friction angle is constant and beta is constant. So basically, I obtain this relationship here, which should be what I find in the web pages. Let me see. Yes. Actually, in the web page, there is a further assumption, which is beta equal to 0, but it's not necessary, actually, in order to reach this conclusion. So, if we knew this constant, given the gamma s and the gamma values and a representative dimension of our unit, I can estimate the critical value of the shear stress. So if I were able then to compute the shear stress by depending on the wave forcing, this formula would allow me to make the verification of stability. Of course, this is something that you may say that it's not really credible, because you may say, how can you, is it reasonable? The assumption, are the assumptions that you made reasonable or not? What are the assumptions that I made? The assumptions that I made are that the forcing F can be expressed as the product of C2 tau d squared, and therefore, you understand, if you have, we will see how we can compute the shear stress, but actually this implies the assumption that the shear stress can be easily computed and is not depending on the characteristic of the fluid motion, which, if you know something of basic hydraulics, it's not really credible, because the shear stress that is caused by a laminar flow is different with respect to the shear stress that is caused by a turbulent flow. So turbulence makes a shear stress that is lower than the laminar flow. And therefore, assuming that this is constant, independent of the characteristic of the motion, independent of the shape of the units, you know, okay, there is a shape factor, but the assumption that a unique shape factor C accounts for all the peculiarities that are given by a specific shape, it's an assumption that may be not reliable. And therefore, what is the idea to check this conclusion? What is the means? What is the way to check this conclusion? The way is lab experiment. So there was a guy called Sheets that decided to go in the lab and make experiments with a flume. Flume. So Shears decided to make experiments with a flume and to check whether this is reliable. And Shears actually was motivated more by the will of checking the stability of grains, Armour grains, in the riverbeds rather than seabeds. But actually the experiment works. And also he worked with a flume that was not really steep, it was close to horizontal. And he pumped the water into the flume. So it's not really the case, it's not really our case, because we have slopes that are significant. But then we will see how we can take slope into account. Now, what did Shears found? First of all, let me anticipate one thing. The way in which we solve these problems, so determining an unknown relationship, that is connecting the dynamics of interconnected physical variables, the usual way that we follow is dimensional analysis. And dimensional analysis, what does it say? It says that if you have a number k of physical variables to be described, physical variables that describe a process like this one, and these physical variables have units that are characterized by n dimensions, and typically in physics, in dynamics, you have length, time, and force. And mass, sorry, length, time, and mass. Mass is related to force, but so typically you have 3 units. So if you have k physical variables that depend on 3 units, then the interdependence between the physical variables can be described by a relationship that is relating k minus n dimensionless quantities. So I have 5 dimensional quantities which I want to relate together. And this quantity, they are dimensional. The dimension can be expressed, I say 5 to give an example, but actually we have 5 here. So we have 5 quantities that govern this process. Perfect. They depend on 3 dimensions, and mass, length, and time. So the relationship between these 5 quantities can be expressed in terms of a relationship between 2 dimensionless variables. This is the premise. Is it clear to you? Just notice that here this is dimensionless. So let's now refer to our problem. How many quantities do we have to describe here? And in order to study the equilibrium, how many physical variables are involved? They are 5, and I look because I don't want to make mistakes, and I want to use the same, otherwise I forget. So basically, it's our physical variables are tau, gamma s minus gamma, rho, mass density of seawater, d, it's the characteristic dimension of the grain of the unit, and v, velocity of fluid particle. And they can be expressed in terms of 3 dimensions. Very good. Now, the conclusion is that the dependence among these 5 variables, and therefore the problem of the equilibrium, can be expressed in terms of a relationship between 2 dimensionless variables. Okay, starting from this theoretical assumption, here you see that I have a dimensionless quantity, it's the Shears number. This ratio here is called Shears number. Why? Because Shears adopted precisely this approach. He said, Okay, I want to describe this process. I have 5 quantities, 3 dimensions. I need 2 dimensionless numbers. And the first one that he proposed was this. This is the Shear's number. Shear's number. But then he realized that we cannot have a constant here. There must be something different. And what is this something different? The something different is the shear Reynolds number, which is called Reynolds star. Did you take fluid mechanics in your bachelor?
Yeah, Reynolds number.
Okay, so you remember the Reynolds number. The Reynolds number is given by the mass density of water, which multiplies the characteristic dimension d, and then you have to put here a velocity, and here let's put the shear velocity. We will see how it is defined, and then I have to put here the kinematic viscosity of water. I hope it is called in English kinematic viscosity, I think so. Okay, and then when if you remove the stars, this would be the Reynolds number for fluid flow, where ρ would be, if it is water, the mass density of water. D is a characteristic dimension of the conduit, of the pipe, for instance, it can be the diameter. And then U would be the velocity of the water into the pipe, and M is the kinematic viscosity of water. Yes, it's kinematic viscosity. And then, if I want instead to express the Reynolds shear number, I have to put here the shear velocity. And the shear velocity is given by U star. Let me use, I write here, U star here. It's equal to, just let me check if the symbols, yes. It's equal to tau divided by rho under square root. Tau is the shear stress that we know. Rho is the mass density of seawater. I will tell you later what you have to remember about this, okay? Don't be too much worried. You don't have to remember everything. But basically, what is the concept that is relevant here? This dimensionless number, which is the Reynolds shear number, it's also called, more precisely, I checked on my website, the particle Reynolds number. This is the correct way to express it. You may also find it in terms of Reynolds shear number, but let's call it, I write on the blackboard, particle Reynolds number. Good. You see that basically this number, along with the Shear's number, it's relating the quantities I am interested in, because the shear velocity is given by tau divided by rho. These are two of the quantities, or 2 of the 5 quantities I am interested in. And then there is, again here, there is the kinematic viscosity of water, which is a constant. And then here I have the shape of the particle. And therefore, given that it's a dimensionless number relating some of my quantities, this is what looks interesting to me. And this was what caught the attention of Reynolds. And then what did Reynolds do? He decided to make flume experiments, as I said. And he decided to build a diagram based on these flume experiments. He made a diagram with this two-dimensionless quantity along the axis. So here he put tau divided by gamma S minus gamma D, and here he put the Reynolds particle number. And then what he did was to pump water into the flume, and for each experiment he increased the velocity of the water flux until the particles started to move. So he was looking at the flume.
So he increased
the velocity of the fluid, of water, and until he saw the particles starting moving. And then, for each critical condition that he found, with different grain size, different condition, for each condition he put a point into the graph. So he made several experiments, several velocities, several grains, several diameters of the particles, and each time that he saw that particles were starting to move, he put a point into the graph. And what he found was that the points originated a cloud that was dispersed around a kind of relationship like this one. And with a lot of points, of course, here and here. Around here, okay? Basically, he noticed that with lower velocities, lower Reynolds numbers, which correspond to low values of U star, which correspond to low values of the shear stress, which means low velocities, he saw that for low velocities, actually the shear stress was higher. And then there was a minimum of the value of the shear number. And then for increasing turbulence, increasing velocities, he found that the equilibrium conditions were reached for a quite constant value of the shear number, and this constant value is 0.056. More or less, some authors say 0.047. The original result of sheets was 0.056, but then some authors corrected. Just focus on the concept. The left part of this graph is laminar flow, which gives unstable conditions. Basically, when you, which gives critical conditions, but it's laminar flow which gives a higher value of the shear number. And then for turbulent, you have a minimum of the shear number for increasing turbulence. But then this is called the transition phase. Then for fully developed turbulence, you get a constant value. Now, if we make the assumption that we are working under full turbulence, which is an assumption that is reasonable in our conditions, we can indeed assume that the shear number is constant. So, Reynolds experiments and Reynolds reasoning, by starting from the recognition, by recognizing that there are two dimensionless numbers governing this process, by recognizing it, through experiments, he came to the conclusion that under turbulence is just one of them governing the process, which is the Shear's number. And then this translates into a practical rule for determining the stability of the Armour unit. We assume turbulence, we put an Armour unit there, provided we are able to estimate tau, we will see how to do that. We have this criteria to check whether the unit is stable under that tau. It is very simple in principle.
Of course, if tau critical is lower than what
yes. Yes, no. I mean, if you get, you plug in tau here. If the result is lower than 0.056,
that is that 0.056 is a constant for every kind of water
in turbulence, under turbulence.
Like
yes, yes, under turbulence.
There isn't the Moody diagram too.
Yeah, in the Moody diagram you have the same situation. It's similar, because the Moody diagram basically tells you what is the friction force under laminar flow and turbulent flow. And you remember that under laminar flow, the friction is much higher. Yes.
Previously, the Moody diagram, I didn't know that this was existed at all.
Because this is a completely different context, because here you have a mobile bed, what we call a mobile bed in river engineering. The Moody diagram instead studies the flow into pipes, but indeed Shears was for sure inspired by the Moody diagram, because he realized for sure that under laminar flow there must be some more friction and therefore more difficult conditions. You see that under laminar flow, in order to ensure stability, you have to, it's a very different situation, and it's more prone to instability, let's say. Okay.
Sorry, under laminar condition, the Shear's number is higher, right?
Yes. Yes.
But this also means that tau critical is higher.
Tau critical is higher, correct. But let me just think at the dimensionless representation. So gamma S and gamma are fixed. And okay, for sure the part below the graph is stable. So you're saying, I understand your reasoning, and
maybe it's less controllable, but it should be, like from my point of view, of course, maybe I'm thinking it wrong, but...
No, you're right. You are right, because it is indeed, you are right, and I tell you why. Because indeed, under laminar conditions, the boundary layer, which is the layer where the water doesn't move, is larger. And therefore, this means that if you have particles sitting on the flow, on the bottom or on the slope here, it is less subjected to forcing. I mean, this is not in contradiction with the Moody diagram, by the way. But yeah, you are right. I was not correct. In laminar conditions, given that you have a larger layer of water that doesn't move, you have more stability. And therefore, what this means, and I try to clarify, I hope that I am. Let's suppose that it's horizontal. In turbulent condition, you have a lot of movement close to the bed. In laminar condition, you have a layer, which is called boundary layer, of water that is basically not moving. And therefore, in order to get the same forcing, you have to get a much larger grain. And therefore, instead here, the size of the grain that is exposed to forcing is lower. And therefore, it's more stable. It's more stable. I'm sorry, I was not correct.
It looks like the worst situation is the semi-turbulent.
Yeah, it's here.
That is quite useful.
Yeah, it's here. And it's here, and this is what the experimental results showed. And with fully developed turbulence, it is constant.
And usually seaside, like in the sea, you have turbulence. Usually.
Yeah, usually yes. When you are in this condition, yes, it's not laminar at all. In the pipes, you may have laminar flow. In the rivers, not. In the pipes, you may have laminar flow. Okay, sorry for the confusion that I made. And here you can see on the blackboard and on the screen the original shield diagram. This is the original, which is it can be published because it's public domain. And if you look at you don't see the values, but anyway, this is what he by hands drew in order to report the result of his experiments. And then, of course, there is to say that we have to consider additional complications. The additional complications are the shield's results are for angle beta that is close to 0. And first. Second, there is the effect of hiding. We studied here a single unit on a flat slope. This is not the situation that we have. We have several units that hide each other. And then there are empirical corrections that we will see after a break of 15 minutes. Okay. Any questions so far?
No, Professor, thank you.
Okay. So see you in 15 minutes, Kashayar.
Thank you, Professor.
Okay, I want to dedicate 5 more minutes to the discussion, especially to clarify the bit of confusion that I made, okay? So first of all, let's redraw the sheets diagram here, where we have the Reynolds number here. By the way, I was not correct. I called it shear Reynolds number. It's better to call it the particle Reynolds number. Or some text say granular, some text may use indeed shear Reynolds number, but I prefer this is the correct one. Reynolds number. Okay. And here I have tau c, tau divided by gamma s minus gamma d. Good. And then I said that we have a similar diagram resulting with here I have 0.056. Now, let's suppose that we have a situation where we compute for a given particle the sheets number and the particle Reynolds number, and I am here. Okay, like let's say here, which means stability. Very good. Now, what happens if I increase the velocity? If I increase the velocity, what happens is that I have Reynolds star that goes up, and tau that goes up. So from this situation, if I increase the velocity, I move in this direction, which means that if I cross the line, then I get instability. Or it may also happen that if I increase velocity, I move in this direction, which means that, okay, in the transition phase I have instability, but then I get under turbulence to stability. Okay? So this explains a little bit better what is the situation. The important thing is that usually we work under turbulence, so we have to stay in this safe zone here. You mentioned the Moody diagram. I think it is interesting because the conclusions are similar, so I was not correct when I said that in laminar flow there is more friction. The Moody diagram. Did you take fluid mechanics in your bachelor?
Yes, I did, and I also did that, but it's not very fresh in my mind.
Yeah, even in mine, so it's more or less the same. So basically we have, in the Moody diagram, we have the Reynolds number on the horizontal axis, and then we have the lambda, which is proportional to friction on the vertical axis. This is laminar flow. Turbulent flow is something like this. So when we pass from laminar flow to turbulent flow, we have actually an increase of friction. And then under full turbulence, we have a decrease, like here. In the transition phase, we have an increase in friction, and then there is a decrease under full turbulence. Okay. Now let's see what happens when we go, when we account for other complexities. So first, let me see, it's not here, okay. First, how can we compute the shear stress? First, usually we consider two situations. shear stress acting on the Armory unit due to currents and the shear stress due to waves. Actually, for groins, groins are close to the coastline, so the effect of currents usually is not very significant. And for breakwaters, they can be a little bit offshore, and then the effect of currents may be significant. In typical situations, it's the driving forcing is that of waves. In typical situations, the forcing due to waves is much higher than the forcing due to currents. But in any case, the literature gives us a couple of relationships under the assumption that we can apply the superimposition principle. So as you see, the total shear stress is given by the sum of the shear stress given to currents and shear stress given to waves. Okay, how to compute them? This is relevant because even if we neglect the effect of currents, we still have to the question of how to estimate the shear stress given to that is due to waves. Okay, so we can use these relationships which say that let's look at waves. These relationships say that the shear stress is proportional to the square of the velocity. As we know that in hydrodynamics, the forcing that fluid flow exerts against an obstacle is proportional to, the pressure is proportional to the square of the velocity. And here, in fact, if we look at this second relationship, U prime is the velocity of seawater particles due to waves. And so we know that before breaking, such velocity is given by the near bottom peak orbital velocity. It's reduced, which can be computed by using this relationship here. Let's not go into the details. This is something that probably you have studied, how to compute the orbital velocity. And where the quantities that you see into the relationship are wave behaviors and wave period, wave spectrum, wavelength, etc. Here, FW is a wave-related friction factor. I go back here. This is the wave-related friction factor. We have a relationship for computing it, and which is given here, which again depends on the roughness of the structure of the groin breakwater, and depends, of course, friction. The friction factor depends, of course, on the roughness of the structure, but it also depends on the wave orbital velocity. But let's also say that when, after breaking, the wave velocity is, the velocity of fluid particles is much higher, and it's given by another empirical relationship which we don't list here. And there is an empirical relationship that makes a difference between run-up and run-down flows. You don't see this empirical relationship here. So to summarize, let's look at this relationship. This is wave shear stress. It's given by 1/2 rho mass density of seawater. FW, you have an empirical relationship to compute it depending on the roughness of the structure and the wave velocity, the velocity of the fluid particle in the waves, and U prime square, U prime, is the velocity of the fluid particles, which is given by the orbital velocity before breaking, and is given by an empirical relationship after breaking, which distinguishes between run-up and run-down. So everything is basically empirical here with some physical fundaments, because you see that indeed there is a, yeah. And also the factor 1/2 is something that if you remember something from fluid mechanics, you may remember. It's, but let's don't go into the details. And then if you look for currents, the relationship is similar, but you have a friction factor that is different, and there is an empirical relationship below in the page to compute it, and U prime is now the velocity of the current. So once that you know the behaviors of waves that are approaching the groin or the breakwater, you can estimate the shear stress, and then you compute you compute tau, and then you go in the Shields diagram and you make your computation. Now, effect of slope. The effect of slope makes a difference. Basically, how it is computed by correcting the shear stress. You see that it is computed a new shear stress TC1, which is given by TC times 2 correction factors, which depend on two slopes, the slope in the longitudinal direction and the slope in the transversal direction. So keep in mind that a groin, a breakwater, can have, it is normally sloped in one direction, which is the direction with the greater slope, and usually it is the slope is max in the side that is opposed to the waves. So if you identify a longitudinal wave direction, which is the direction of the waves, the direction of wave propagation, then the max slope of the breakwater is along the same direction. But you may have a slope also in the transversal direction. And therefore, depending on the direction of waves, you get a slope that is in the same direction of waves, longitudinal direction, and a slope that is in the perpendicular direction, the transversal direction. So you have two slopes. One of them may be 0, and the other one may be something like 45 degrees would be 1, 1, and it is often less than 45 degrees, as you know. So depending on these two slopes, then you get the two factors, two correction factors, K beta and K beta 1, depending on the two angles, beta and beta 1, and depending on the friction angle phi. So you compute these two factors, and then you correct the shear stress. This is something that you don't have to remember. Then I will make a summary of what is, in my opinion, what you should remember on this, but you can already, I can already anticipate you have to remember the concepts and maybe the expression leading to the computation of the Shields number. This is what I suggest, but I will make a summary on this. And then we have the effect of hiding. So what we first, hiding, what does it mean, hiding? It means that if you have a situation where the units have different size, then you get some of the units that get hidden behind a unit of greater size. There are correction factors for this, which depend on the diversity of the grain diameter. I'm just mentioning this effect, no empirical formula, okay? But why? Because hiding actually is not a relevant effect for the design of groins and breakwater. Usually groins and breakwater are composed by using units that have more or less similar size. What is indeed relevant is the effect of the shape of the Armory units. We have introduced a shape coefficient, C. On the other hand, there are shapes that are particularly appropriate for building, like tetrapods, for building groins, breakwaters. They are particularly suited to ensure stability because they can block each other easily. And for these shapes, you need to estimate the shape coefficient in a dedicated way and possibly through lab experiments. These the shapes that are typically used are tetrapods. There is a link here which gives an idea of how they are done. But there are several types of tetrapods, and here you see some examples, but there are several different shapes. Some of them are made in order to, by taking a crossed shape. These are what are indeed typically called tetrapods. And you see that indeed these can benefit from an increased stability due to their shape. And you have tables in the literature that give suggestions in order to optimize, to identify the value of the coefficients that are used in the different formulas for taking shape into account. For instance, you see here in this picture that there is you see that the shapes are indeed extremely diverse, and often they also put together different shapes in order to optimize the reciprocal blocking of each unit. Okay, now why I think the Shields method is interesting. It is interesting, first of all, it is used. There is a reference here to Van Rijn, from where I took these notes. And I think it is useful because it is based, the physical basis is really important. It is a method that allows you to better understand how the whole process works. What should you remember about this? First, I would say that a typical question that I ask at the exam is to talk about the stability of the Armory units with the Shield methods. If you're able to reproduce this diagram, which I don't think it requires a lot of learning by memory, that would be great. And if you can make these steps, computational steps, to get to the empirical formulation of the Shields equation, that would be really great. And it's enough. And you don't have to remember all the reasonings that I made on the dimensional analysis, and you don't have to remember anything related to the Moody diagram or to this empirical relationship to compute tau. It's not really important. If you remember that tau depends on the square of the velocity of the fluid particles, that's fine. And if you remember that tau may be given by waves plus currents, that's perfectly fine. But don't learn these relationships here, or the correction factors for slope. Hiding is not there, but it's not needed. Okay. What is really, I think, educational is this scheme here, which allows to understand the functioning of the process and allows you to remember important things like what is a stabilizing force, what is a destabilizing force, and remember that the stress depends on the square of the velocity. This is what I suggest to you. This is a question that I ask quite frequently. Now, the remaining of my webpage talks about empirical methods, which I think you already know. And in particular, the Hudson formula, which I think you saw with Professor Archetti, which is, at the end of the story, similar. It's a similar criteria. This is derived in a completely empirical way, but if you look at what are the influencing variables, okay, here you have wave behaviors instead of shear stress as driving force. And of course, wave behaviors are more easily determined with respect to shear stress, where you have to compute the velocity of the fluid particles. It is a bit more complicated. But actually, I think that an interesting exercise is to recognize in the Hudson formula that, I mean, more or less, you see here the slope, and KD, which is an empirical stability coefficient, which you need because it's an empirical formula, and then you have the wave height. Okay. So I think that that's it for the stability of the Armory units.
Can I ask something?
Yes.
I don't think it's a very good question.
No, it is.
But the shear that we are using in order to develop these formulas is the surface shear of the wave or the current.
No, it's the bottom shear stress.
The bottom.
Yeah. So if you have before breaking, the shear stress at the bottom is almost zero. If you are in deep ocean, and but you have anyway an orbital movement of the particles. You remember that in the waves you have this kind of orbital movement. This is causing, if there is an interaction with the bottom, it's causing some shear stress on the bottom, which is usually very reduced because it's a very low velocity. So in these conditions, maybe that if you have currents, the shear stress of currents is higher than that. After breaking is a completely different story because you know that the transfer of energy is transformed in transfer of mass, and after breaking you have a significant velocity. Any other question?
No, sir.
Okay, very good.
So sorry, the shear stress of the wave is taken from the lower part?
Yes, yes. It is given by the contact surface between the waves and the structure. Of course, when there is a structure, maybe that this contact surface is very close to the surface of water. If you think at wave run up, it is really given after breaking by movement of water at the surface. Okay. But if you think at breakwater in deep water, what matters is indeed the way. Yeah.
Because the sediments are at the bottom as well.
Yeah,
So
correct. Correct.
We can relate, I suppose, the shear in the surface to the shear at the bottom.
Yes, because there is a formula for computing the orbital velocity, which depends on the depth of the particle. And therefore, basically, given that the shear stress is also related to the velocity, you can relate it. But of course, you have shear stress not between particles and particles. You have shear stress between the water and the structure or the sea bottom. Okay, so you can't say that half width, half depth, you have shear stress. There is no shear stress there, and there is some shear stress between particle and particle, but this is not what you are interested in because particles, okay, they are moved by the upper particles, but you don't have any action against the structures, so you are not interested in that. Okay. Now, actually, I think after this lecture, I think we have two more because today is 30. Yes, we have two more. Okay, so two more, but I'm not sure if April 13 we have lectures. Yeah, probably yes. Probably yes. Okay. Probably yes, because I think it is, I'm not really sure, but I think that I got it in my diary. So I just want to check because, let me see. Yes, I got it in my diary. So April 13, we have lectures. So we should end it before Easter. Okay. And okay, so as I said, we have 2 more lectures, and there are a couple and then there is another half an hour, more than half an hour, 40 minutes today. And I wanted to talk during the remaining time that we have about these issues. First of all, there is something that I would like to make today, which is related to design of breakwaters. I think this is information that is additional. There is part of the information in that lecture that is already part of your background, but I think there are a few new considerations that I would like to I would like to make. And then there is a lecture that is not still linked here, which is dedicated to dredging in Harbour basins. And then I want to close with a discussion on climate change, the effect of climate change on sea-related processes. So I think we can start with design of breakwaters, and then I have to remember to put the link to the dredging. And your presentation today gave to me the inspiration, but not the SEER, that I probably could include in the list of these lectures something related to water quality, because I think it may be indeed interesting, because it is an emerging problem. And okay, we will see. So design of breakwaters. As I said, there is part of this lecture is already in your background. So you know what is a breakwater. I think that also you know what are the different types of breakwaters. And there are the rubble mount breakwaters, and then we can build breakwaters with air bubble curtains, so we can use air bubbles. And also we can build up artificial beaches, which act as a breakwater. And there are floating breakwaters. I think you also know this. I think Professor Archetti talked about this structure. Perfect. And so we can skip it. And also you know that the breakwaters can be submerged or emerging. We can skip it. And now, there is a description of the various forms. I think there is also a link here, which is interesting because tetrapods, it's the link that we saw before. There is a link to Wikipedia to dolos, which are these one, which are different from tetrapods. And also there is, I think, there is this scheme here.
Sorry, but floating breakwaters, they are effective only when there is the crash, or also when the wave is not, because if they are, they work as a buoyancy, they just move with the wave, like.
Yeah, but they have a different period of movement. So basically, they don't go up and down with the waves because they have more inertia, and therefore, basically, their movement, their up and down is much smoothed. And so they, in a way, they flatten the waves, because if you take a body that is going up and down with a wave, a frequency that is different from that of waves, basically the result behind the breakwater is a merge of the two frequencies, and the waves gets dampened.
Nice.
Yeah.
I didn't expect that.
Yeah, because they are floating with, you know, it's like when you see a ship in the waves, you see that indeed against the side of the ship, you still see the waves, because the ship doesn't go up and down at the same frequency of waves. So basically, this is why you have these. These are useful.
So maybe you have to study the frequency of the
Yes.
water. Maybe
Yes.
for the critical situation, the right frequency.
Yes, and the advantage is that for calm conditions, they basically, first of all, some of them you can inflate and deflate them. So some of them may even stay on the sea bottom. And then when you need them, you inflate air and they emerge. Because of course, when there is no air inside, they go along the sea bottom, and when you put air, they emerge. And even when they emerge, if you have a movement of waves that is very slow with very low frequency, then they go up and down together with the waves, and they don't perturbate the movement of waves. They are just floating, as you said, at the same frequency. But then when the frequency of wave increases, then they dampen the waves. And it is interesting, even if sometimes, when they are inflated and they emerge, they look more artificial than a rubble mound breakwater. Because, if you use boulders to make breakwaters, okay, you perceive that it's artificial, but still it is something that is less impacting than a bubble that is floating over the water. But what is interesting is the fact that in calm conditions you can just remove them. This is interesting. They are more expensive because rubble mound breakwaters, they are not expensive. They are very durable. They don't need a huge maintenance, and
maybe they are useful, the floating ones, when there is a high depth.
Yeah, maybe when there is.
Yeah. Make maybe a very tall.
Yeah. Maybe, yes, okay. Just 1 second, because okay, here we are. Okay. And as I said, the shapes, I think that Professor Archetti already talked about it. Yes. And what I want to, and also I think that you studied also the structure, how the structure of a breakwater is built, with a core, with a secondary armor, a primary armor. So we can, usually I don't ask anything related to that. What we can discuss is run-up and overtopping. Did you discuss with Professor Archetti about run-up? So the formulas for estimating the wave run-up, they are already known to you.
We talked about it. I cannot remember about the formulas at this moment.
Okay. Anyway, basically, there is nothing to really learn here. There is a description of what are the determinants of run-up. So wave height, the depth at the toe of the slope, so water depth, and the porosity of the slope. If, of course, if the porosity increases, then you have less run-up. And then there is the roughness of the slope, same thing, because if the porosity increases, you have a much more permeability. The roughness of the slope and the wave period, it's a determinant, the slope of the structure and the slope of the shore. And then there are several formulas that, depending on all or some of these variables, give you an estimate of the run-up. Why is the run-up important? For several reasons. And here there is an example of a formula. The run-up is important for several reasons, because, of course, you may be interested in estimating if a breakwater could be overtopped or not. This is the first reason why it's important. And it is important especially if the top of the breakwater is accessible by people. And for instance, you may have a sidewalk on the top. Keep in mind that sometimes breakwaters are also used as berths. So it's indeed the case that in some situations we may have a sidewalk above there. And today there is a renewed interest in run-up because there are several projects that aim to use wave run-up for producing energy. I'm not sure whether Professor Archetti mentioned this project to you.
Today we did the vertical wall, which had the custom, where the wave is like a chemical, and the wave enters and pushes the air inside the chamber, which makes a turner turbine, and works also opposite direction when.
And it was Professor Archetti talking about this. Okay, this is still in the domain of research because there are several researches that are being carried out now at the international level on this. Because indeed there is a huge amount of energy in waves that we don't use usually because we just wait for the waves breaking, and this is indeed an opportunity for renewable energy. And okay, so this is why we are interested, because in order to design these plants, these turbines, etc., we need to estimate the run-up that we can expect, because of course the higher the run-up and the higher the potential energy, because of course water reaches a higher elevation, and therefore it's the amount of energy that can be retrieved is directly proportional to that. Okay, and also another interesting thing, which I'm not sure if Professor Archetti mentioned to you, is the wave transmission, which means that breakwaters, depending on their features, don't completely eliminate waves, but in most of the cases they reduce the wave height and therefore reduce the energy. They absorb part of the energy, but part of the energy is passed through. And so in the lee zone, which means the zone that is comprised between the breakwater and the coast, we still expect some waves, even if the breakwater is continuous, because, as I said, the breakwater is partly permeable. And therefore, we have to expect some transmission. Let me check why. Okay. Okay, and so how to estimate the height of waves on the lee side? Usually there is an empirical formula which estimates the wave transmission coefficient, KT, which you see here, and it's simply defined as the ratio of the transmitted wave height to the incident wave height. So if HI is the incident wave height, we put it at the denominator. At the numerator we have the wave height in the lee side, and we expect that KT is less than 1. And so basically, and there is another determinant, and if we take, we denote with zeta ZC, the elevation of the crest of the breakwater over still water level. So you get mean elevation of the sea surface in still conditions. And then you estimate the elevation of the breakwater above this mean water level, and you denote it as ZC. These are the rule of thumb that are suggested. So if you have Z divided by wave height on the offshore side, that is lower than, it's more than 3/4, which means that you have the elevation of the breakwater which is comparable to the wave height, comparable, it's 3/4 means 0.7 of it, then you have minor waves generated on the lee side. If instead you have that ZC is equal to 0, anyway, you have an effect, a dampening effect that is caused by the submerged part of the breakwater. So basically you have a reduction of about 1/2. And if you have ZC divided by wave height that is less than minus 1/2, so submerged breakwater, then KT is greater than 0.75. These are the rules of thumb that allow you, these are very simple, you don't have to remember them, but allow you to get an idea of what is the wave height that you may expect in the lee side. Okay, and there are several empirical relationships to estimate KT. You can forget about them. There is the van der Meer formula, it's widely popular, where depending on the characteristic of the breakwater and the incident waves, you get to an estimate. And there is another more complicated formula, again by van der Meer. Keep in mind that van der Meer worked mainly through empirical experiments, as usual. And let's forget about the details. And now let's focus on one final thing, that is the water setup induced by breakwaters. And this is interesting. And you know, breakwaters creates a barrier between two water fronts. One is very energetic and the other one is less energetic. And so the difference in energy causes the transfer of water volumes in the lee side. So if you have a very huge difference in energy between the two sides, you may expect that on the lee side, the deficit of energy is compensated with some more potential energy. So what what happens is that you have a flow of water through the breakwater or for overtopping, and you have a water level in the lee side that is higher than, you have a mean water level on the lee side that is higher than the mean water level in the offshore side. And this is something that it's significant. It's not just a matter of a few centimeters. It can be very significant when you have a very energetic environment, which causes also a return flow. So when the energy in the offshore side goes down, then you have a return flow, of course, from the lee side to the sea side. And recent findings highlighted that the setup originated by partially submerged or submerged breakwaters may originate currents in the longshore direction. So this is something interesting, and which may trigger unexpected beach erosion. So usually what happens, you have, imagine the presence of a long breakwater. You have difference in energy along the breakwater. So behind, in the lee side, in the land side of the breakwater, you have this increased water level, but you have difference in energy. You have also in the lee side differences in water level, and then there is a transfer of water in the longshore direction. Because it's easier, I mean, in the offshore side you have a lot of energy, so water cannot go back. But in the longshore direction, there is it's a calm situation, and therefore you can get a longer shore current, which causes beach erosion. This is indeed something interesting, because indeed you protect the beaches with breakwaters when there is a lot of energy that you are expecting. But then you build a breakwater, and this energy causes an increase of water level close to the beach, and then the water goes along the coast, because otherwise, of course, if there is a lot of energy, cannot go back in the offshore side, and causes erosion for a longshore sediment transport. And this has been noticed in recent investigations. Okay, and there are empirical relationships again, and to estimate this delta sigma, which is the difference in elevation in between the two sides. And of course, you don't have.
But this erosion is anyway less than the one that would exist in the case there was not the breakwater, I suppose.
So say again the question, sorry.
The erosion due to this change in the level is anyway less than
yes,
you would have if there was not the water.
Yes, but what is important to take into account is that it's a different phenomenon with respect to what you are trying to mitigate, because breakwaters basically try to mitigate the cross-shore sediment transport, which is extremely, I mean, it's very often it's prevailing over the longshore one. And then in order to mitigate it, of course, you solve one problem. On the one hand, you solve the problem. On the other hand, you have a side effect. And the side effect is to be considered among the other side effects. Another side effect is water pollution, because, of course, in the lee side, you have a calm situation, and then you cannot remove pollutants. And but this is interesting because it's something that you wouldn't expect. It's not immediate to get that you may get this longshore current, which is, I mean, it depends on the situation if it's important or not. Longshore currents usually they are in a way concerning if they can last for a long time. If they are there only for a short time, I mean, their erosive potential, it's not very much intensive. And then, as I said, I think that this relationship is not to be learned anyway. I just mentioning this effect because I think it is interesting, and I think it is useful if you remember it. It's if you remember the possible presence of this effect. Okay. I think that it's okay, stability of Armory units, we just discussed it. So I think this is what I wanted to say for this particular topic.
And sorry, groins, so perpendicular breakwaters, have the same problem, or probably less?
No, less than that, because I mean, the groins basically they contrast the longshore movement of waves, and it's less energetic than the cross-shore movement. So you don't notice it, and it is groins are, you know, it's also if you look at how these structures built, you understand that breakwaters are conceived to resist to a forcing that is more important with respect to the forcing of groins. And groins, sometimes you see that they are they are permeable structures made by woody elements, and it's usually there is not this problem. And of course, it depends on the situation. Sometimes, as you showed, no, I think you showed it, no, or you showed it for the port of Rotterdam. There was this structure that it was placed where the coastline makes an angle. So they defined it as a breakwater, and but it is perpendicular to at least a part of the coastline. So sometimes you cannot really. Yeah, because this was placed at an angle. But in this picture, I think it was interesting. I didn't ask you to look it back at it. I think it was interesting because you can see the effect on wave diffraction, I think. The effect on the waves on it. It was clear. I mean, it was clear what they wanted to achieve, because they wanted to protect, you know, the entrance of the port. And I think also this must be very deep, because this is, I mean, very huge ships get into there.
20 meters.
20 meters deep.
Like the highest depth of the port is 24.
Okay.
Some points get to 24 meters depth for the ship to enter, and they're not mainly on the entrance, but they need to go there to the ship. So.
But what is, I'm not sure, what is the max of the depth that the hull, or I'm not sure if the hull of a ship can reach, because for...
Like the new ships, the biggest ones, the cargo ship, they are, like for the stability, I don't know, but I imagine since they go over the water, I don't know, 50 meters, they need to have at least 15 meters on the other way to have stability. Otherwise, I don't know.
Yeah, it
but
depends.
I think 18 meters, something like that.
18.
18 meters, yes, of that.
So even the big ships, those that are 300 meters long, they don't exceed. We could easily check.
Yeah, exactly.
We could easily check. But also the stability depends on the ballast. So it may be that they use a lot of ballast, and they don't need a huge depth. Sorry? Yeah. The width.
No, I was wrong.
What is the English term for the depth of, it is the drought, yeah, it is the drought, but I'm not sure if drought is the correct, yeah, I think drought maybe.
Yeah, drought is the...
Yeah, what in Italian is called pescaggio, qualcosa del genere.
Opera morta.
Ok.
Sì, opera viva, opera morta. But the max here in Italy says 21 meters.
21. So this is why the port of Rotterdam is 24, because they want to, okay, I see. Okay. Just, I'm checking, I put a link to a useful reference at the end of the lecture. I put a link to a useful reference that I found for the design of breakwaters, and which is a commercial publication, but I think it is interesting. It describes the different shapes, and also it gives, it is 32 pages, so it's quite long, and it gives also some indication on the design.
Archetti told us that some of the boulders and their shapes are patented.
Yeah, they are patented, yeah, correct.
I didn't like it.
Correct.
I didn't know about this business.
Yeah, they are patented because it's, you know, it is an interesting question. What is the optimal shape that you should give to a unit in order to ensure the max stability? Because if it is too complicated, then it can break. And if it breaks, then of course it falls out of the context that we considered for the design. And so, because you may say, okay, the more I complicate the structure, and then the better it is. But then, if you make a structure, a shape that is too complicated, then you have to work in order to put them into place, to locate them. And ideally, you don't want to spend much time and locate each piece, also because you have to work underwater. So, and you want to be able to be very quick and an easy allocation of these pieces. On the other hand, you want them to block each other quite effectively, and you want that they are strong enough in order to remain locked when there is a huge forcing. So it is an interesting question. It is, and they make a lot of experiments, in lab experiments, and also field experiments in in a real field, in a real situation, and so you can understand why it is patented. Okay, now for these 10 minutes, I want to introduce dredging. I forgot the link here, so I am going to last year's page, but I will put the link soon. If you go to the last year pages, you see that there is dredging in Harbour basins, which is what I want to discuss with you. And first, a premise, why this issue is important. Harbour basins are subjected to siltation or sedimentation. Why? Because we try to create calm conditions there. And therefore, if we create calm conditions, of course, there is the deposition of sediments. And also keep into account that there are several harbors that are located at the estuaries or of rivers. This is a typical situation because it is an ideal situation where to build an harbor, but the river also delivers sediments. And again, the harbor is protected by currents, protected by waves. So in a natural situation, if you have the river delivering sediments, then there is the equilibrium with the ocean, waves, currents, etc., that it's a secular equilibrium that created the shape of the coastline, and therefore it is quite stable. But when you protect the harbor, then you perturbate this equilibrium, and there might be the need for dredging the harbor basin. There is also an interesting thing to keep into account, that when you operate an harbor, there is very often release of materials, like gravel, like material that is transported by the ships, and unfortunately, very often this material is polluted. And therefore, you have a mix of natural siltation, and you have a mix of loose material that is lost when unloading and loading ships. And this material is polluted. It's polluted because, for instance, in some cases you may lose some oil or things like this, but it is also polluted because typically the harbor is a polluted environment, as we saw in the presentation. And therefore, you have this material that is settling down on the sea bottom, which makes the operation of the port activities inefficient, and you have to remove it. But when you remove it, there is the problem of displacing it, because even if it was clean material, even in this case, it's a problem to displace it, because you cannot release in a single point in the ocean, you cannot release the dredging material. So there are solutions, which we will see, of ships that are dredging, and then they go offshore and they distribute the release of the material that they dredged, but not in a single point. They are obliged not to pass a certain concentration, because even a concentration of mud that is above a certain limit causes problem to the ecology of the marine environment. And also this material is then transported by waves in high concentration somewhere, which is causing some perturbation, because the volume, it's really important. We are talking of important volumes of materials. And therefore, how to make these operations and how to displace the material is becoming really an issue. And when we devised the content, when we decided to identify the content of this degree program, we had a meeting with the managers of the port in Ravenna, which is an important port. You show the table, it's one of the, I think it was the 5th or the 6th in Italy in your table. And so we asked them, what are the problems that you would like that we deal with? Because what is the type of profile you are looking for? And one of the things they said, which I was surprised, because I didn't think that here there was this problem, but they said, we have a problem which is dredging, how to displace the material that we dredge, because we have a lot of harbors, a lot of berths that need dredging, but we don't know how to displace this material. And this is what motivated me to prepare this lecture. And basically, the premise that I made is summarized by this picture. So harbor basins are protected, as you can see here. And if you put breakwaters or groins, they are even more protected. And therefore, you have a low energy environment where you have siltation. And therefore, the problem is how to operate. And what are the factors that are influencing the siltation rate? There are several factors that you can easily imagine, and they are listed here. Just keep in mind that this could be a question at the exam. So what are the factors affecting the siltation in harbor basin? So distance from open sea, the area of the harbor basin, the area of the entrance in the basin, tidal range and duration, and the peak tidal current outside the entrance, outside concentration of sediments, of course, and density difference inside and outside the basin, because keep in mind that also the sediments can move by following the gradient, so for diffusion. And here we are not considering the river. Probably this picture would have been more comprehensive if I put a river here. This is a picture that I've done by hands. And, but this is something that you may mention also, the presence of the sediment dynamics originated by rivers into the harbor basins or in the close vicinity. And now, harbor siltation, some indications, is higher, factors up to the value of 5, in salt and brackish water condition than in freshwater conditions, for the higher concentration of sediment and the generation of stratified flow in the presence of salt water. Let me check if I have a PowerPoint presentation for this, just 1 second. Not yet, okay. So, of course, the saltwater conditions is what is interesting to us. And so, how can we understand this process? So how can we make prediction? How can we design dredging operations? This is a question. So what is the frequency? And keep in mind that when you dredge, you increase the siltation potential because you create like a hole. And therefore, it's clear that you have a gradient of siltation that is increased after dredging. So what is the best strategy to plan these operations? What are the technical guidelines to follow? And this is the main question, which implies some sediment dynamics modeling, of course, understanding of how sediment dynamics is evolving and how it is influenced by the presence of the harbor, the coastal protections, and the dredging operation, and the ship traffic. Okay, I would say that this is subject for the next time. I think we can stop here, and if you have any questions on what we discussed today, you are welcome.
Yeah, the siltation. Could you repeat the definition?
Yeah, it's siltation is deposition of sediment. Is sediment settling down? And let me just see if siltation meaning. I made a mistake. Okay. Siltation is water pollution caused by particulate terrestrial clastic material with a particle size dominated by silt or clay. It refers to both the increased concentration of suspended sediments and to the increased accumulation of fine sediments on bottoms where they are undesirable. This is an example of siltation, and it is considered pollution, as you see.
Yeah, because you told us first lesson that silt and clay, they absorb pollutant.
Pollutant, yes, pollutant, correct. Okay. Kajayar, I hope you could attend the lecture in an efficient way.
Thank you, Professor.
Okay, thanks a lot for your attendance.
Thank you. Have a good day.
You too.